Okay. Okay, welcome back, friends, to the next lecture of heat transfer. We will continue from where we left off yesterday during the class in radiation heat transfer. We had just started talking about exchange between gray surfaces, right? And to start with, we first took two parallel plates which are infinite in size in the two lateral directions, and we derived an expression for radiant exchange between these two surfaces, where one surface has an area, I mean, forget area because these are infinite, has a temperature of T1 and emissivity of epsilon 1. And similarly, the other surface has an area of T2, has a temperature of T2 and emissivity of epsilon 2. We figured out that the heat exchange by radiation, net heat exchange, because there will be emission from both surfaces and absorption at the other surface, okay, when it reaches. So the net heat flux, the radiant heat flux, that is heat transfer per unit area, is given by a very simple closed form expression, which, as I said, is a very well-known expression and everybody should remember that. It is sigma T1 to the power 4 minus T2 to the power 4 divided by 1 over epsilon 1 plus 1 over epsilon 2 minus 1. Okay, very easy to remember. At the top is the difference between their emissive powers. I mean, sorry, the difference of their black surface emissive powers, okay, EBs, at that temperature. And at the bottom is 1 plus 1 over epsilon 1 plus 1 over epsilon 2 minus 1. Easy to remember. Okay, very close form, very nice. So, and I said as a result that this is a very well-known expression which people should remember. Okay. So this is where we stopped yesterday, right? And this is what we had derived, isn't it? Okay. So today what we will do is we will take off from here and do you can say it's a problem, but it's a very well-known problem, which is known as radiation shield. I had alluded to it yesterday. So I will talk about a problem which is called radiation shield. As the name suggests, my aim here is to reduce this radiation exchange that I see at the top. How can I do that? I have two plates and I want to minimize the heat loss or heat exchange by radiation. So therefore I need a shield, as we have said. Okay. So what is it? So let us go back here. This was my surface 1. Sorry. And this was my surface 2. This was epsilon 2 P2. And this is epsilon 1 P1. Now the radiation shield, you consider this system and you insert a thin, opaque, infinite plate in between. Okay, which has got emissivity of E3 on both surfaces. Okay, so therefore consider system of two parallel plates, infinite plates. Okay, a thin, opaque, important. Okay, infinite plate is inserted between A1 and A2. Okay, with emissivity epsilon 3 on both surfaces. Okay, it's a sheet, so it has two surfaces, top and bottom. The emissivity is epsilon 3. Okay, so try to understand what will happen. What will happen is that the shield, this is called the radiation shield. This shield at steady state will acquire a temperature T3, which we don't know. Okay, what that temperature we don't know, but we can guess that it will be something somewhere between T1 and T2. But what is more important is such that whatever it receives from 1 is given to 2. Q over A 1 to 3 is equal to Q over A 3 to 2. Okay. And this is also going to be Q over A coming from 1, because whatever it gets from 1, it intercepts and gives it to 2. Okay. So this is the function of radiation shield. So what can I write? Therefore, I can write, which implies, therefore, Q of A by 1. What would be Q by A 1 to 3? Again, two infinite plates separated by a distance, parallel plates. One at T1, the other at T3. I don't know what T3 is, but I can write exactly this. Sigma 1 to 3 would be T1 to the power 4 minus T3 to the power 4 divided by 1 over epsilon 1 plus 1 over epsilon 3 minus 1. Agree? And that is also equal to sigma T3 to the power 4 minus T2 to the power 4 1 over epsilon 3 plus 1 over epsilon 2 minus 1. Okay. My aim is to find out what is Q, I mean this expression Q by A. What is the heat that is lost by plate 1? Net heat loss from plate 1 by radiation. Okay. So therefore, which will come to the radiation shield and then in turn be transmitted or be transferred to the surface 2. So to eliminate T3, which is my unknown, eliminating T3 to the power 4, we can write, what can we write? I mean, we have to eliminate T3 to the power 4. We have to add up the numerators, isn't it? So therefore, I can write 1 over sigma Q by A1 times, just add up the others. Okay, 1 over epsilon 1 plus 1 over epsilon 3 minus 1 plus 1 over epsilon 3 plus 1 over epsilon 2 minus 1. Okay, this would be equal to T1 to the power 4 minus T2 to the power 4. Okay, so all I've done is I've taken the numerators to the other side of, sorry, denominators to the other side, to the left handmost term, and divided by sigma. Okay. So look at how beautiful this term turns out to be. Or therefore, Q by A1 is sigma T1 to the power 4 minus T2 to the power 4 divided by, what is it? 1 over epsilon 1 plus 1 over epsilon 2 minus, sorry, plus 2 over epsilon 3 minus 2. Okay. Now, initially, what was my heat loss? This one, 1 over epsilon 1 plus 1 over epsilon 2 minus 1. Now, what is my heat loss? I have added a 2 over epsilon 3 minus 1 to the denominator. Okay. Now, 2 over epsilon 3 definitely is greater than 2. Or in other words, plus 2 into 1 minus 1 by epsilon 3 minus 1, right? 1 over epsilon 3 is definitely greater than 1 because epsilon 3 is less than 1. Okay. So therefore, the denominator has become larger, which means that this heat loss has become smaller. This is definitely less than sigma T1 to the power 4 minus T2 to the power 4 divided by 1 over epsilon 1 plus 1 over epsilon 2 minus 1. Right? So therefore, this means that inclusion of the shield, of the radiation shield, reduces the net heat loss by radiation. Okay, this is routinely, regularly used in spacecrafts because you don't want to lose the heat. Outside temperature is at, outside space is at very, very low temperature. Okay. All right. Now, if you can take a special case, if epsilon 1, epsilon 2, epsilon 3 are all equal, then what happens? Then this becomes 2 by epsilon minus 1. 2 or 4 by epsilon minus 2. So like that. You can now keep on putting more number of shields. Actually, when people put radiation shields, there's a series of them, one after the other. Okay. And what you see is each shield in turn reduces the temperature, reduces the heat loss. Okay. So you'll keep on adding. If you have another surface with epsilon 4, you will have plus 2 over epsilon 4 minus another 2. So minus another 1. Okay. Again, you have another epsilon 5. You will again have 1 over epsilon 5 plus 1 over 2 over epsilon 5 minus 1. So this denominator keeps on adding. Okay. All right. And you can work that out. I'm not doing it, but you can work that out. If I have if I bring in one more radiation shield in between, either at the top or at the bottom, you will get the same. You can work out what is the net heat loss by radiation using the same approach. Okay. Yeah, I think that's about it. Okay. Now what we will do is we will take up another example. And that is radiation exchange in the annulus of two concentric cylinders. Okay. Achha, one more thing I want to say is here, as you can see, the placement of the radiation shield does not matter. Whether you put it where I have drawn, you take it closer to surface 1, closer to surface 2, it doesn't matter. Okay. So keep that in mind. If you are considering pure radiation, the placement of the radiation shield between the two plates doesn't matter as long as it is in between. All right. So concentric cylinders, tubes, whatever you may call. So let us first understand what is happening. So first draw here. I'm not going to write as much. You guys already know what we are doing. You can take more notes if you want based on what I speak. So here is one tube. And here is one more. This is the outer tube. The inner tube. Outer tube. Inner tube at a temperature as before, T1, epsilon 1. Outer tube, T2, epsilon 2. Okay. Let us say that this is radius R1, and this is radius R2. Sorry. Okay. Definitely this is surface 1, and this is surface 2. So what is going to happen? The radiation exchange is going to happen between the outer surface of the inner tube and the inner surface of the outer tube, that is in the annulus. Okay. So heat exchange in the annulus. Okay. Assume T1 greater than T2. That's okay. Doesn't matter. So radiation will go back and forth in the annulus, starting from surface 1. It will reach surface 2, and then successively get absorbed and reflected at the surface it encounters, just like before. Okay. So what we would like to do is, we would like to get a geometric progression like series in the previous case. But here, it is a bit more complicated. Why? Because these are not parallel plates. The view factors with respect to each other or with respect to itself is not 0. So let us see what we want to do. Okay. Okay. Let us consider calculate Q1 prime and Q2 prime, that is per unit length. Okay. So let us do that. If this is my center, extremely sorry about my drawing. I hope you have, by now you are used to it. Okay. So friends, please listen to this very, very carefully. Okay. So the first what we will do is, maybe I should have drawn it a little. No, it's okay. Let us consider a ray Okay, let us consider a ray E1. Okay, E1. Okay. Now, when it reaches surface 2, what will happen? First thing you know that a part of it will be absorbed, and that would be epsilon 2 times E1. And the rest will be reflected. Okay, and this is where it becomes important to understand. Rest will be reflected. And this reflected ray will go where? Right? Reflected ray will go over where? Earlier it was just going back to surface 2, but here it is going to have two parts. Part of it will go back to surface 1, part of it will be reflected back to surface 2 itself, because the shape factor of surface 2 with respect to itself is not 0. Okay, so keep that in mind. Now let me come here. This is look, I'm taking notes is fine, but if you don't understand this progression, you will not be able to figure out later. So you have to understand every step here. Okay, so note f1 to 2 is equal to 1. It's a convex surface. Right? But f2 to 1 will be a1 by a2 times f1 to 2. f1 to 2 is 1. a1 by a2. What is the area? Surface area of the inner tube, outer surface of the inner tube? 2 pi r1l, where l is the length. And what is the surface area of the outermost surface area of the inner surface of the outer tube? 2 pi r2l. So a1 by a2 is equal to also r1 by r2. Okay. So this will be equals to a1 by a2 or r1 by r2. Keep this in mind. All right. Now let us come back to what we were seeing here. So therefore, this reflected ray will have two parts. One that goes back to surface 1, and the other which gets reflected to itself. Okay. So this friend is going to be what? a1 by a2 times 1 minus epsilon 2 times E1. Okay. And this friend is going to be 1 minus a1 by a2 times 1 minus epsilon 2 times E1. Now imagine this guy again, when it reaches surface 1, part of it gets absorbed and the rest of it gets reflected. Sorry. How much gets reflected? 1 minus epsilon 1 times what went? a1 by a2 times 1 minus epsilon 2 times E1. Agree? I'll call this as 1 and I will call this as 2. Both of these come back to surface 2. Okay? And therefore, from here, what gets absorbed would be epsilon 2. Sorry, let me use this other thing. Will be epsilon. Oh, okay, sorry. Black was good enough because I've used black here. So what gets absorbed here again? Would be epsilon 2 times this 1 plus 2. Okay. And likewise, then again, the remaining 1 minus epsilon 2 will again get reflected. Part of it will go to surface 1, rest will go to surface 2, and this continues. So therefore, I'll quickly write ray E1 emitted by A1 reaches A2. Epsilon 2 E1 is absorbed. Rest is reflected. Partly to A1 and rest to A2. Okay. And so on. So this is the first set of absorption and reflection. Okay. So based on this, what I can write is the rate at which radiation emitted by A1, radiation is emitted by A1 and absorbed at A2 is equal to what? The first one was, of course, the amount of radiation that is emitted is A1 E1. The first was epsilon 2 plus second one was 1 minus epsilon 1 times A1 A2 times 1 minus epsilon 2 times epsilon 2. Okay. If you just do this 1 plus 2, that's what you will get. Okay. Plus, you will then find 1 minus epsilon 1 A1 by A2 whole squared. Again, this next iteration, if you go, you will find this 1 minus epsilon 2 whole squared, epsilon 2 plus blah, 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 blah. Okay. So then again, a geometric series, and each of it is less than 1. Because if I take A1, E1, epsilon 2 out, I have 1 plus x squared plus blah, 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 where x is equal to 1 minus epsilon 1 A1 by A2 times 1 minus epsilon 2, which has to be less than 1 because each of these is less than 1. So I can write therefore A1 E1 epsilon 2 divided by Okay, if you just expand this basically. Okay, so now similarly, this is more of a mathematical exercise, I know. So that's why there's not much to explain. For rate at which radiation is emitted by 2 and absorbed at E1. Yeah, you can do this as an exercise. It's not going to be exactly symmetric, but you can do it. That would be equal to E1 E2 epsilon 1 divided by exactly the same denominator. Okay, you can do this as a home exercise. Actually, it will be easier than I did the more complicated one. Okay. So therefore, Q1 to 2, one thing please note that unlike the previous case, here because the areas are different, we are talking about the total heat exchange instead of heat flux. Okay. Q1 to 2 would be the difference. So A1 epsilon 2 E1 minus epsilon 1 E2 divided by the denominator. Okay. So now what I want to do is I want to remove the dependence of the epsilon. Okay. So what can I therefore write? E1, E2 we know. So what I will do is E1 would be what? E1 is epsilon 1 sigma T1 to the power 4 and E2 is epsilon 2 sigma T2 to the power 4. So epsilon 2, epsilon 1, epsilon 2, that multiplier is there in both terms. Divide by A1, all that stuff, mumbo jumbo. Therefore, what I will get is, you don't need to divide by A1 actually, keep it there. Doesn't matter. Sigma A1 divided by, look at this, so beautiful. 1 over epsilon 1 plus A1 over A2, 1 over epsilon. So 1 over epsilon 2 minus 1. Okay. So since only two surfaces are involved, therefore Q1 equals to Q2 equals to Q1 to 2 is equal to sigma A1 T1 to the power 4 minus T2 to the power 4 divided by 1 over epsilon 1 plus A1 by A2 1 over epsilon 2 minus 1. This, my friend, is probably the most important expression. With a wide variety, with wide range of validity. With your kind permission, thank you. Okay. So one thing, you can just look at this equation for a while. Now make it A1 equals to A2. Do you get back the previous expression for two parallel plates? You do, right? Okay. So let us look at this. Let us just think back and see what all we did. We took two annular spheres and look at the radiation exchange between the outer surface of the inner sphere and inner surface of the outer sphere. Clear? And we found this expression. So tell me, during this entire expression, apart from writing once that A1 by A2 will become R1 by R2, which we did not use. We always dealt with A1 and A2 only hereafter. So did we ever use the fact that these are cylinders? Probably not. We have used it indirectly in the sense that F1 to 2 is 1 and F2 to 1 is A1 by A2. Other than that, we have not, right? So therefore, if you consider two concentric spheres, of radii R1 and R2, okay? So here also, F1, sorry, F1 to 2 equals to 1 and F2 to 1 equals to A1 by A2, except A1 by A2 will be R1 squared by R2 squared, okay? The expression derived above holds here as well. Acha, what if the two tubes or spheres are not concentric? Did we ever use the concentricity part? We did not. Or whatever we use for the derivation, was the fact that they have the same central axis or the center in case of sphere? Is it necessary? Okay. Same relation is valid as long as F1 to 2 is 1, F2 to 1 is A1 by A2. Okay. Why spheres and tubes or cylinders? Any two surface two surface enclosure where F1 2 equals to 1 and F2 1 equals to A1 by A2, Okay, we'll be fine. Okay, for example, a flat surface and a hemisphere, A2, A1. Any problem? No? Exactly same thing. What we were doing in that annulus, we will do the same thing here. A1 goes to A2, part of it comes back to A1, part of it goes back to A2. Then what came back to A1 will get reflected back to A2. Same thing. One box inside the other. Okay. 2D or 3D. If it's a semicircular tube, that's fine. If it is a flat, it's the base of a sphere and a hemisphere. It's a circular base and a hemisphere around. Here also, okay, rectangular tube or square tube inside a tube, or a cube inside another bigger cube inside a room. Okay, so although we derived the relation for concentric tubes, the relation is valid for a variety of scenarios, provided that F12 equals to 1, that one shape factor is 1, the other shape factor is A1 by A2. Okay, and it's an enclosure, definitely. Two surface enclosure. Okay. Special case. See how beautiful it is coming out to be. The special case is A2 is way, way bigger than A1. Okay, such that A1 by A2, sorry, A2 is way, way bigger than A1, tends to 0. If that is the case, what happens? This Q1 just put it down there and see what you get. Sigma A1 T1 to the power 4 minus T2 to the power 4. Okay? Then it was 1 plus A1, 1 over A1, plus what was it? A1 by A2. Then 1 over epsilon 2 minus 1. This is what we had. But what we are saying is this is tending to 0. So what do you get? What you get is what you knew about radiation before this course. Sigma epsilon 1 T1 T1 to the power 4 minus T2 to the power 4. Okay, sorry, my OneNote is misbehaving a little bit, but you see what you just got. Sigma epsilon 1 A1 T1 to the power 4 minus T2 to the power 4. This is what we had. This is what we knew about radiation heat exchange before coming to this course. But what we have learned now is that expression actually is valid for a very, very special case. Okay. Of two surfaces exchanging radiation, where the view factor of surface 1 to surface 2 is 1, and the area of 2 is infinitely large compared to the area of A1. So for example, yeah, if I am a person standing in the middle of a field and vast expanse of sky around me. So whatever I am exchanging with the outer space, yeah, I can use this. Okay. If it's a big furnace and I have a small iron ball inside at a high temperature, Okay, not furnace. Let us say a cold storage chamber. Furnace is also fine. In which case the heat transfer will not be from 1 to 2, but 2 to 1. So the heat absorbed would be T2 to the power 4 minus T1 to the power 4. Clear? So let me close my OneNote and relaunch again because it is not behaving properly. Okay. So friends, I hope you have now understood this whole scenario. Okay. Now, as I said, I deliberately, probably I could have saved one lecture. Okay. If I had just given you or taught you a very mathematical tool, but I wanted to go through this ray tracing thing for you to understand actually physically what happens. I can get this expression very easily using what we are going to learn now, which is called the radiation network method. But that is the last part. The last topic under radiation. Okay. So to start with, what we will do is, and this will be mathematical. Okay. This will be mathematical, but still, to start with, let me explain to you something. Whatever we have learned so far. This is a surface. Okay. Now, what happens? On this surface, you have an irradiation H which is falling. Okay. And then you have something else which is leaving this surface. Okay. I'm going to call that J. Now, what is J? That is the amount of radiant energy leaving the surface. And that has two components. One is what it emits, which as we know is epsilon EB, or epsilon sigma T1 T to the power 4, plus what it reflects, plus rho H. Agree? So therefore, H is irradiation. Okay, which is the total radiation flux incident on the surface. And J is called, it has a name, which is called the radiosity, which is the total radiation flux. Leaving the surface. Okay. Assume. Okay, sorry. So therefore, what is the net heat flux? Net heat flux going out of the surface is J minus H. So assume surface to be opaque. Okay, so therefore, which implies tau equal to 0. Therefore, rho will be 1 minus epsilon. Therefore, J is going to be epsilon EB plus 1 minus epsilon H. Okay. Now, net energy net flux, I would say, net, okay, not total, net would be Q double prime. Just 1 minute, let me connect the battery, connect the charger, sorry. Q double prime Q over A is equal to J minus H. So what is that? Epsilon EB plus 1 minus epsilon H minus H. I can do a little more mumbo jumbo here. I can write this as J minus epsilon EB divided by 1 minus epsilon. Okay. And then J into 1 minus epsilon, etc., etc. And what finally I can write it as, or Q is equal to epsilon A divided by 1 minus epsilon EB minus J. Or you can also write it as EB minus J divided by okay. So the last thing that I'm going to write here is, and to end this class is, look at this. If you think about this, okay. Interpretation is that if the denominator is considered as a resistance and the numerator as a potential difference. Okay. If I were a black surface, I would have given out just EB. But because I'm not a black surface, there is something like a surface resistance which is prohibiting it. Okay, this is the interpretation. We will write it again. So the way we are going to just today end by drawing a picture where I'm trying to say that I have 2 points. This is EB, this is J. EB is the source because it's a surface. So this is like a surface resistance, which is determining how much is the heat flux. If epsilon was 1, then J would have been equal to EB because rho would have been 0 and nothing. If epsilon is 1, if it's a black surface, then EB and J, they collapse and the surface resistance goes to 0. Clear? So this is the interpretation. We'll take it off from here tomorrow. Okay. So let me stop sharing. And then what you will see is, through this interpretation, I can find out what is the net exchange between two surfaces. Okay. And you will see that each of the expressions that we derived can come out from there. Okay, but it would be a mathematical exercise. That's why physical you won't have a feel of what is actually happening in the space. So that's why I did those two derivations between infinite plates and these concentric cylinders. Okay, thank you very much. That's it for today. We will meet again on Monday. But before that, our class test will be at 9 a.m. on Saturday, 2nd October, Saturday, 9 a.m. Syllabus is conduction heat transfer. Okay, let me stop the recording. All the best for your exam. And I think you should be fine. Okay, thank you.